my name is Henk Witte. I work for a company Groenholland in the Netherlands, and we are specialists in ground source heat pump systems, both the ground heat exchanger and the heat pump systems themselves. And my my friend Michael Lauermann from AIT will be the co-presenter. He's also an important part of this work package within the project, together with Edith Haslinger from the same institute. And I also want to mention one of the other main partners in this work package, EuroCat, the Catalonian Institute of Research that has been doing work within this work package. So we want to talk with you in this session about ground heat exchangers and heat pumps. And the motivation is that with the ground as a source for a heat pump, we can have highly efficient heating and cooling. But although for newly built buildings, it is fairly common to use ground source heat pumps. For existing buildings, so for retrofit applications, there are not so many solutions because it is complicated to install a ground heat exchanger in an existing situation. And then if we look at non-urban areas, so not densely populated areas, we are also looking for low-cost solutions, low-cost and easy to install ground heat exchangers. For instance, Slinky, or in German Ringgraben, ring collectors, horizontal, and also earth basket ground heat exchangers. And the problem with this is actually that there is not an integrated advanced engineering design tool. So although for vertical borehole heat exchangers and some other softwares for special type of heat exchangers do exist, there is not an integrated engineering approach for all these different type of heat exchangers, and therefore it's also very difficult to evaluate which installation would be best suited for your specific application. So in the presentation, we want to take a little bit a look at the design process. How do we develop an integrated design approach? Because design, it's not only calculation, it is also thinking about your boundary conditions and doing some sensitivity analysis and making sure that the design is properly documented. Then we will talk about new calculation methods for different and more complex ground heat exchanger topologies. One of the questions there is also how to deal with things like laminar turbulent transition, which affects the thermal resistance between the fluid and the ground. So it's an important aspect of the operation of such a system. We also talk a little bit about the far field modeling. So how do heat exchangers at larger distances affect each other? All of this has been supported by a lot of laboratory experiments and computational fluid dynamics modeling. So Michael will talk about that. Validation of all the methodologies that we've developed, and then we start looking at performance analysis. So how do the different type of heat exchangers perform? We take a little look at the engineering tool that has been developed. Then Michael will talk more about the heat pump developments within the GEOFIT project. And then as a wrap up, we'll have a little peek at the field laboratory at 2 demo sites where we've been installing a monitoring system for the ground heat exchangers. So the first part, the ground heat exchanger design process. What is the goal of a design? Well, very simply put, we want to know how large the heat exchanger has to be able to give us a certain heating and cooling from the ground, an energy demand, a capacity, so not only the energy in kilowatt hours, but also the capacity in kilowatt, the instantaneous capacity that we want to take out of the ground, and then the required performance. So what is the performance, the ratio between energy input and energy output that we want to achieve, which is of course very closely coupled to the temperature from the ground, from the source, and the temperature in the sink in the building. Other boundary conditions are of course also important, like soil thermal parameters, the drilling conditions or excavating conditions themselves, and the available space. So again, design is not just performing calculations, but it's an iterative process where we look at all these different aspects and try to find out what the best, most robust solution for our system will be. So seasonal performance and energy savings achieved, that is of course one of the main things why we want to use this type of technology. We want to save energy so that we can reach our climate goals, have less greenhouse gas emissions. For the end user, we have an economic benefit, but we have to make sure that we can calculate this correctly under different boundary conditions, such as soil thermal parameters, climate, and building characteristics. One aspect is obviously also the technical and operational life of the system. We're using the ground, which is of course a system that is also used for other purposes. And if we want to save CO2 emissions and energy, it is important that we can achieve that for a long time. So the life expectancy of components and the design itself has to be um, uh, yeah, correlated with this life, like 25 to 50 years of the system itself. We also want to take a look at balancing between the installed capacity and the energy that we want to take out of the ground. If you have a low energy load with a high capacity, obviously this capacity will be very important in the design. But if we take out the same amount of energy with a smaller capacity, the whole design changes, and we can achieve this with a smaller ground heat exchanger. At the end, we want also to look at the sensitivity and the final validation of the final design, because we have to make a lot of choices, and some of the aspects we're quite sure about, other aspects perhaps we are not so sure about, and we can investigate how this would affect our design and then decide if we want to have a better analysis of that part of the system. This can be the geology, the thermal characteristics of the ground, but quite often we also find that, for instance, the energy demand analysis of the building is lacking in detail and in quality. So what we've been doing in the project is to develop a kind of roadmap for a project design, where we look at the feasibility and the permits that are required, because if you're not allowed to install a ground source heat exchanger, for instance, in a water protection area, then it is not much use to continue with that type of technology. Then the second step is collecting and evaluating the data needed for the design, the energy demand profile, the soil conditions, the type of heat pump that we're going to use, etc. And then we go into the thermal and hydraulic design of the system itself. So what are the design parameters and boundary conditions? Things like what temperature do we want to achieve in the ground source in heating and cooling operation, but also, for instance, a limit on drilling depth or other boundary conditions that we can think of. Then we want to take a look at the different ground heat exchanger solutions that we could apply. Are we going to go for a horizontal shallow one, or are we going to go for a vertical deep one? Once we've done all these decisions, we're going to do the calculations. And in the calculations, we have to look at the local process, the individual ground heat exchanger, and then we're talking mainly about the construction of the borehole or the slinky type heat exchanger, and looking at the parameters such as fluid flow, fluid type, and how that translates to the borehole thermal resistance. And then we have the global process, where we start looking at interactions between individual loops, and at the end of the day, also the sensitivity of this design. Part of the design calculation is also the hydraulic part, mainly the pressure drop and the pumping power associated with this. And like I said, at the end, we want to document the design process and the results of the design for the end user, for the owner of the system, but also, for instance, for regulatory bodies to make sure that they know what has been installed. So one example, and we go a little bit more into detail when we start talking about the heat pump system, is how are we going to deal with the total energy demand profile that we have. So this is about the hybridization, which often in retrofit case we will have, that we so what we want to do here is, for instance, take a look at how much of the total energy are we going to cover by the heat pump, and how much of the total energy are we going to cover with the auxiliary system, like a gas-fired boiler or other systems that are in place. And what we can see here, let me put my pointer to laser. What we can see here is that, for instance, we can decide to do everything with a heat pump. Another possibility is to do part with the heat pump, and then once we exceed a certain capacity, we switch over completely to the auxiliary system. This we would do, for instance, if also we want to increase the temperature in the auxiliary system from a low temperature to a higher temperature to achieve a higher capacity in the emission system. And we can also do it in a different way that I hope Michael will explain a bit later. Another example in the design process is to take a look at how robust, what the quality of our design is. And then often we have things like the peak load duration. So we're looking at the capacity, but also how long that capacity has to be supplied continuously. And then we can see that if in the design we take a small amount of hours for the continuous peak load duration, and in the operation of the building, the peak load would be much longer than we anticipated, that we get a big change in temperature. On the other hand, if we already have a longer peak load in the design and the peak load time increases, the effect on the temperature is very small in this area, for instance. So, this is just a trade-off between a longer heat exchanger and more robustness with regard to peak load duration, and a shorter heat exchanger that can have a shorter peak load but not a very much longer peak load. So it depends on the system design whether that is an intelligent choice or not. Another example of sensitivity is to look at the effect of different parameters. For instance, the average ground temperature, thermal conductivity of the soil, the base load heating, distance between boreholes, etc. And then we can change that parameter by a certain percentage, for instance 10 or 20%, and look at the effect on the length of the ground heat exchanger that is required. So for instance, in this example, we see that the base load for cooling has a very high effect. That means that if we could achieve a better balance between heating and cooling load, that we would get a smaller heat exchanger, but also a more robust design. In the other example here, we see, for instance, that the average ground temperature can have a large effect. In that case, we could say, okay, if we do a test borehole on site, or we have other data available from site where we can have a better parameterization, a better estimate of average ground temperature, that would be a good idea. And then finally, we want to document the design. So in the design report that we've generated, we have all these kind of tables where the actual design and choices that have been made can be clearly documented. So this was the first section talking about the design and the design framework. And I would like to ask if there are any questions about this part. No? Okay. If there are no questions, then we will proceed with the computational framework. So in the computational framework, like I indicated before, we have to deal with the global process, which is talking about the temperature evolution in the ground. And then we have the temperature at the ground heat exchanger wall, but also the interaction between all the different ground heat exchangers in the specific ground volume. Furthermore, because we're talking about shallow heat exchangers, we need to include the near surface seasonal temperature variations. In summer, the shallow earth will be warmer. In winter, it will be cooler. And if the whole heat exchanger is at shallow depth, these variations need to be considered. And on the other hand, if we do vertical boreholes, we also have to take into account that there may be a deep geothermal gradient where the deeper we go, the warmer it gets. It's usually between, let's say, 15 and 30 Kelvin per kilometer depth. On the other hand, we have a local process. So this is the process in and around the heat exchanger itself, where we're dealing with the thermal resistance between the fluid and the ground, and also the pressure drop, which affects the pumping power. So here we have to deal with equations to calculate the thermal resistance for very different geometries. In a ring, you can imagine that the flow path is completely different than in a straight pipe. We also have to deal with something important like the turbulent laminar boundary, because at turbulent flow, we get a low thermal resistance, but a higher pressure drop. And with a laminar flow, we get a higher thermal resistance, but a lower pressure drop. So we need to have this equation set to calculate it in a consistent way for all the different type of geometries that we encounter. And one of the things that we did there also is to develop correlations for temperature dependent fluid properties, because a system can operate both in heating mode and in cooling mode. And then obviously things like especially viscosity of the fluid will be very different between low and high temperature operation. The next thing was to have this standardized methodology for the ground source heat exchanger design calculations. And we are mainly looking at conductive heat flow in the ground. So we're not considering groundwater flow. We're at this stage also not considering phase changes in the ground itself. Basically, what we did is develop a solver for temperature effect at a certain distance from the ground heat exchanger for all the different geometries that we have. And then we have a solver for the fluid temperature as function of the capacity and the thermal resistance. So it's a pretty basic approach that's been used in many other engineering tools as well, only we've extended it to all the different ground heat exchangers that we can think of. The main things are superposition of temperature effects in space and time, we'll get to that a bit later, and superposition of long-term and short-term response as well. What is needed for this is also a decomposition of the energy demand profile, because with the superposition methodology and the methodology, the analytical models that we use, we can only calculate it for a constant energy demand. So we have to use a superposition of different energy steps. And to speed up the calculations, we use a G-function approach. So the first thing is to take a look at the decomposition. If we have here an energy demand for 1 month, 2 months. So in this month, we have a certain heat load. In the second month, we have a higher heat load. In the third month, an even higher one. And then in the fourth month, a lower one. We have to calculate the first time step for the whole duration of the simulation. So we calculate this load here. And then we say, okay, in quarter 2, in the second month, we have a higher load. So the difference between these two, we calculate, and then we add it to the effect of the first one, starting in month 2. For month 3, we have still higher heating demand. So we calculate that from month 3, and we add it to the solution of month 1 and month 2 that run through the whole period. And in this way, we can calculate the exact energy profile for all the months and years that we are interested in. This is the principle of superposition of a decomposed energy demand profile. This can take a long time, as you can imagine. So the basic idea here is that we can do this for only one step change in energy demand, and then calculate the typical response for the whole heat exchanger system. And this typical response is translated to what's called a G function. And then with the G function, we can not do all the detailed calculations with the analytical formula, with the analytical equation, but we can very quickly calculate the response of the system over the whole time period. So our challenge was to develop all the G functions for the analytical functions for all the different ground heat exchangers. And what we've been using is the finite line source equation, the finite line source analytical solution, which is basically the workhorse for ground heater exchanger design. And fortunately, of course, for the 1D case, the vertical borehole heat exchanger, this equation already exists for a long time and is well known. And even for the horizontal and the ring type of heat exchanger, it has been developed and published, for instance, based on research from the United States. So what we have done mainly is implement these two in our engineering tool and then add it from 1D to 2D to 3D, the earth basket type heat exchanger in the same standardized methodology. How does it work, the finite line source? Well, if we imagine that this is, let's say, the soil surface, and here we have the ground volume, then we have here a borehole heat exchanger, and we can have point sources of heat that we then integrate over the whole length of the borehole. Now, obviously, at the surface, we do not want to have any temperature change induced by the borehole itself. So on top of that, we have what's called mirror sources with a negative heat demand. And if we integrate over that whole system, we get a solution for this point, for instance, in the ground, integrated, all these effects of the individual point sources can be calculated. The same type of approach can be used for a ring type heat exchanger, where here we have a ring and then here we have another ring, so a slinky type or ring graben, and then the mirror sources are again on top of the surface defined and cancel out slightly the closer you are to the surface. And we can do that for flat rings, but we can also do that for horizontally, vertically oriented rings. I'm not going to explain all the equations because that goes much too deep into the theory. For the earth baskets, then what we did is that we took the ring type heat exchanger and we said, okay, we can use this as a kind of stack, a layer of pancakes in the soil, and then we have another stack at a certain distance, also of a layer of pancakes in the soil. And in this way, we can calculate the effect of an earth basket heat exchanger. So again, exactly the same type of solution, only extended to 3 dimensions. Then the next step is to take a look at the thermal resistance between the fluid and the ground. For a vertical borehole, we have a typical U-pipe configuration. This is a top view. Here we have the borehole radius with the borehole filling. Here we have 2 pipes, one going down and one going up. And you can imagine that there are a lot of different processes going on here. But at the end, we can say there is a temperature difference between the fluid in the pipes and the wall of the borehole, which depends on the whole structure of this system. The same for a concentric borehole, where we have a small dimension pipe in a larger dimension pipe, a different set of equations, but again we have a fluid temperature difference between the fluid in the heat exchanger and the ground. Now for the ring type and for the spiral type, for the earth basket type heat exchanger, the system is slightly different because we're dealing not with straight pipes, but with rings. And with rings, we get a difference in speed of the fluid in the inner radius and the outer radius, which has to be accounted for. So the equations become slightly more complicated. So we took a look at this, and again, we developed a framework using equations that are valid for all the different types of conditions that we encounter and the different types of geometries that we encounter. And then we have to take a look especially at the critical Reynolds, and then we can find the correct Nusselt correlation for our thermal resistance and pressure drop equation. So this is just a little overview of all the equations that have been developed for that. One of the important questions then is how to deal with turbulent laminar flow, because we know that in laminar flow we get a high thermal resistance and in turbulent flow we have a low thermal resistance, and also the pressure drop changes. This is mainly characterized by what's called the Reynolds number. And then for straight pipes, we see that the critical Reynolds number is usually taken at 2300. And this means that in a lot of design software, there is a big difference if you have a Reynolds number of 2299 and a Reynolds number of 2300. This is one problem. The other problem is that for curved pipes, it's more complex, as the critical Reynolds number, it's not a fixed value, but it actually depends on the ratio between the ring diameter and the pipe diameter. And we get this equation for the critical Reynolds number in a curved pipe. Looking at that, we can see here that the critical Reynolds number, depending on the ratio between the inner and the outer diameter, or the inner diameter of the pipe and the ring diameter, it's relatively high. Here we can see it's not 2300, but already above 4000. So in a spiral heat exchanger, it's actually relatively difficult to achieve turbulent flow, real turbulent flow. Is this important? Is this a problem? Well, if we start looking at how this then translates into the thermal resistance, we can see that actually the thermal resistance for the even low Reynolds numbers, the thermal resistance here, is actually relatively low. So in a spiral heat exchanger, due to the geometry, the thermal resistance is always quite low, and we have a low, even at low laminar flow Reynolds numbers. If we look at the straight pipe, the blue line here is how the theory says that it should go. So at 2300, we have a very critical boundary between a high thermal resistance here and a low thermal resistance there. Now we know from experiments and also from other research that there is very often a transition zone between laminar and turbulent flow, and that is actually around 2300. So what we could do is include a transition zone, for instance, between a Reynolds of 1800 and 2500, and then have a much smoother transition there from the laminar to turbulent flow regime. And this is what we actually implemented in our software. Then we go to the next part, and then Michael will take over and he will talk about the lab experiments and computational fluid dynamics modeling. Okay, Michael.
So I will show you, let's say, the part we did regarding the lab experiments and the CFD modeling, kind of the basis for the validating the already mentioned G-function approach or FLS method in order to have a speed up computational experience. So checking now, yeah. So regarding the method, so we started out with testing of the thermal efficiency of those spiral shaped collectors. So this was done by setting up lab experiments with a model of a spiral shaped collector. So those experiments then were validated, or it's basically the other way around. The CFD were validated with those experiments, the so-called near field CFD with the simulation package fluid. And finally, those experiments and also the CFD results, those were the basis for the development of this engineering tool for the configuration of different spiral-shaped collectors, as well as the simulation of the thermal behavior of those collectors when they are installed in the field. Yeah? So basically the method was first lab experiments, then CFD of the near field behavior, let's say validation of those lab experiments. And with those results, we took a look at far field, how they perform in field when we have a certain array of such spiral shaped collectors, and also let's say build the basis for this engineering design tool. Yeah. Before I go into very detail here, to click away the laser pointer. Not allowing me. Sorry. Ah, yeah, now it's working. So I first would like to introduce you to the people behind this laboratory experiment. So Henk already mentioned Edith Haslinger, a colleague from AIT, who is a dedicated geothermal expert, geophysics. She helped with the concept how we do those experiments. On the left, you see my colleague Stefan Kling, who did his master thesis in that part. Let's say also help with the concept and also build up those experiments. So we had the opportunity to take him after his master thesis. So he's now on a regular work contract at AIT, and I'm very glad of that. And on the right side, it's myself. So this is more or less the core team of those experiments. But of course, we also had more people working on that. Yeah? So what you see here is as a first step, we build a model of an Earth basket type heat exchangers, and we put that in a rather large box, which you'll see in detail in the next slide. So we installed fiber optics for temperature measurements, as well as several sensors for soil moisture and temperature throughout the entire box. Yeah? Then we filled the box carefully with cable sand, which is one type of sediment for the backfilling of spiral collectors. In the end, we had a box with roughly 1 cubic meter of sand, which weighed about 2 tons. And the box, together with the collector model and also the sensors, was then placed in the climate chamber at the AIT research facilities, because we want to keep constant boundary conditions. So our aim was to test, in the end, several loop types, different variations of loop pitches, and also different soil or sediment types, also at different temperatures and at different heat flow rates. Yeah, this was, of course, an ambitious goal. And in the end, and as it is in science, we had to learn that all those variations in the big box, that was logistically way too time consuming. It would be complex and really slow. So therefore we developed an additional experiment. So that is on the right of that slide. We call that the so-called thermopipe. So it's just a simple experiment. And with this so-called thermopipe, of course, it has a smaller mass, and we delivered faster results, and also the handling, of course, was much easier, because this helped us when we changed the sediment types. So, of course, there is no collector model in that thermopipe, but it helped us to validate more or less the material properties. We also took out of those measurements. So in these pictures, you see the details of those earth basket models. You see an orange cable which is swirling around. So this orange cable is the heating cable. So we built up the experiments with heat injection into our soil, into the sandbox. This makes the experiment, of course, much easier, because heat extraction you can do it just by electrical current. And this is how we characterized our experiments. So you see the orange cable is the heating cable, and above and below this heating cable, so this is might seen here a little bit, you see gray cables above and below of that heating cable. So those cables are so-called fiber optic cables, which allow for distributed temperature sensing. So we have placed a lot of fiber optic cables along and inside this whole box. So you see, okay, we have fiber optic cables on the heating cable. You also see those green mesh, let's say, surfaces. So those are one green is on the inside of this model, because our model is the orange-shaped heating cable. So we have one domain inside this heating cable, one domain right on the heating cable, and one domain outside the heating cable, where we measure with this distributed temperature sensing option. We also place those fiber optics on the outer walls. We also placed, let's say, conventional temperature sensors, PT1000, in our box. We also placed a moisture measurement sensors. So in the end, we have a data acquisition system which has roughly 26 temperature sensors. We have 12 moisture sensors inside. We have in total 200 meters fiber optic cables in our system. We do the control and also the post processing with LabVIEW and with Python, and we took also soil samples before and after the measurement of each configuration. So what was looking like this at a scheme, in reality, our setup in terms of control and data acquisition looks like this. You see here the computer with the lab view environment for collecting the data and also for controlling the amount of heat, for instance, we inject. Here's the computer for the DTS system, for the distributed temperature sensing. On the other side, we have those input-output cards and a lot of cables, as you see here. So this is credit for Stefan Kling of his work, and he also wrote this into his master thesis. If you want to have a look, a more detailed look on that, just go to the GEOFIT webpage and look at the publications. There you will find his master thesis. Considering the moisture content, so the thermal physical properties were measured in our thermophysics lab. So we determined the soil moisture, but not only the moisture, also the thermal conductivity, the heat capacity, and the density. So we took samples with a so-called soil auger, that is this tool here. So you just put it in your domain and get out some samples. You see here the locations where we took the samples before and after the measurement, and then we determined all the parameters for all the sediment variations we did, which were most moist and dry sand, and also moist and dry humus. So this is the range of our soil variations. You see here, out of this thermophysical measurements, we calculated the thermal diffusivity, which is a crucial parameter for the CFD calculations and for numerical calculations in general. So after one measurement campaign, so basically what we had was this temperature curve over one fiber optic cable. So you see 200 meters in length, and basically you see here those steep rising and falling, but you can figure out, okay, of course those are three domains what we see here. So that is why we took into one direction and then we went back. That is why we have always two peaks. So it's basically you can map those into one, and this is what you get out. So you get the temperature information with a certain resolution along the length, and what we had to do was to translate this information into X, Y, Z coordinates in order to have a temperature resolution within our 1 cubic meter basket. So this is what you see here. Yeah. So this are the points where we have the temperature information. The blue one is, let's say, the small basket inside the heating cable, our model. Then the orange one is right on the model, and the green basket, the bigger one, is a little outside of the model. We also have temperature values around here, and this is on the right side. You see a distribution of the temperatures after a certain time. You see here at the initial conditions, we have all the temperature levels at roughly 10 degrees. So this reflects our boundary condition in our climate chamber. And then you see, for instance, after 48 hours and after 90 hours, how the temperature is evolving during time over those baskets. Yeah? Of course, right on the heating cable, we have the hottest temperatures. So the temperature is plotted on the x-axis here, and the Z coordination on the y-axis. So of course, the hottest temperatures are on the cable itself. Then we have the blue one that is in the center. So of course, it's not that hot as on the cable itself, but it has also some storage effect here, and of course less heat losses than the basket on the outer side. That is the green curve. Yeah? So this is what we get out of our measurements. And when we take a look at the results, at the final results in brief, so at the top left, you see those experimentally measured temperatures, as I mentioned before. The experiment was run until we reached a thermal equilibrium, which was roughly 800,000 seconds or 9 days. So overall, it shows a good match between the experiment and the model at all measuring points. The best fit is, of course, in the center of the model, while we have a slight deviation towards the boundaries at the top. So this is the deviation in the upper half of the box, which may be credited to sand consolidation when we moved the box. You know, we had to move it inside the climate chamber, and when you move like a sand filled volume, then of course you have a little consolidation effect, which you cannot do anything again. So when we look at the diagram on the bottom left, this one, so we see the temperature development of the conventional temperature sensors during the experiment. The temperature sensor right in the center of the basket shows the highest temperature during the experiment. Again, the match between the measured, so the measured are the solid lines, and the simulated are the dashed lines. Turns out is very good. We have a rapid increase, of course, with passing time, can be observed in the early transient stage. So this is this part, while near steady state conditions, it's clearly visible after probably 9 days. So initially, the temperature difference, as discussed at the discussed PT1000 sensor positions, seemed quite large. However, at time zero, at the initial conditions, a distinct offset at all three sensor positions can be observed. So this is a calibration issue, more or less. On the top right, you see the CFD results of that reference basket. So what we did was modeling the heating cable, which formed this spiral-shaped geometry. So we modeled, we exactly copied this experiment on in our CFD package. And this CFD package has been validated with the big box experiment. So those four figures show the temperature distribution at 4 points in time. Yeah, that means 14 hours, 28 hours, 3.5 days, and roughly 9 days when we reach the steady state. And we also did calculations with a slinkit type and also with double baskets. Yeah? But of course, this is our reference. This is what we can compare with the experiment, and those further geometries. Okay, this is just a result because we cannot do all the variations with experiments, so we had to rely on the CFD code. But this code is validated with at least with the reference basket. Yeah? So taking a look at the transient result. So what I have shown you now, those four figures is shown here in the video, and there you see the temperature evolution over time. How we see of course the hotspots on the heat exchanger itself, and how the temperature decrease is formed until up to the boundary conditions. You see on the 10-degree boundary conditions at the walls. So this is basically what we can do, and this is what we validated with the experiments. Yeah? So out of those near field analysis, it is also crucial to take a look on let's say arrays of such spiral-shaped collectors or earth baskets. So the colleagues from EureCut, in person of Manuel, they did far field simulations where they took our result from the near field simulations and took that as a boundary conditions for their far field analysis. In that way, it's not needed to mesh and to mimic this detailed geometry of the spiral shape. So what they did solely was use that area here, this surface, and put our boundary conditions as their input for those far field analysis. Yeah? So what we get out of this far field analysis, that we can determine the interaction between those ground heat exchangers under different arrangements. So what Manuel did was 3 different sets of arrangements. He of course used the soil properties and the thermal parameters, what we also did for the near field. He took a look at the effect of the spacing of those heat exchangers for one given arrangement, and also for one given arrangement, taking a look at the different soil conditions. And he also compared long-term numerical simulations for one arrangement for 3 different climate zones. Yeah? Although we are pretty much at the end of the project, those last analyses are still ongoing. Yes. So taking a look at those configurations, so we figured out three arrangements, one regular arrangement for those rectangles. Arrangement 2 would be one basket in between those rectangular shape, and one V shaped arrangement. So there are 3 arrangements to take a look on and to analyze how they perform over time with such earth baskets. So, sorry, too quick. So basically what you see here are the temperature contours for those 3 different arrangements. These simulations represent the temperature fields after roughly 100 days. Of course, the soil properties are the same as for the AIT calculations. We see that after 100 days, the arrangement 1, there are still some areas unaffected. So we're still in our initial condition here. And of course, and that is obvious, when you put those earth baskets closer together, that you have more interaction compared to when we have a bigger distance between them. So this is, let's say, the qualitative analysis. When we take a closer look for arrangement 2, which is shown here, so after 7 days with different spacing for this arrangement 2, you see that with a spacing of 2 diameters of one earth baskets up to 10 diameters, that of course the temperature in between 2 baskets is not, or far less affected when you put the baskets more at a more bigger distance rather than you have them close together. So this is, let's say, when you think about it, it's obvious that you get such results. For us, it is important to have a quantitative result on that, and to use this far field analysis to drive or to get the boundary conditions for those G-function approach to analyze such arrangements of earth baskets. Of course, not with CFD, but with pretty much faster calculation methods. Yeah. So this was for the experimental and for the CFD part. I also wait a little bit if there is some question.
Hi, Michael. This is Marco. No question at the moment, so you can move forward.
Okay.
Okay.
Then it's my turn again. Henk here. And we start taking a look at the validation of the analytical solutions that we've developed. So mainly the CFD calculations have been used to validate the results of the analytical solutions for the earth basket type heat exchanger, because for the vertical boreholes and for the slinky type heat exchanger, we could already do validation using existing software. So the validation, one of the questions, of course, is you've seen in the presentation by Michael that in the CFD we have an actual helical shape, so it's a spiral. But of course, like I explained, we approach it by a stack of rings. So one of the question is that not an oversimplification of the geometry? And then the second question is actually how well do we fit between the temperature calculated with the FLS and the temperature calculated with the CFD. Now, an additional problem is then that because the geometry is slightly different, we cannot compare directly between the analytical solution and the CFD solution, because the position of the ring is slightly different, and you can also imagine that the inclination of the ring makes a difference. So what we did is define a point cloud around, at small distances and slightly larger distances, a point cloud around the earth basket type heat exchanger, and then compare the CFD solution and the analytical solution for that point cloud, because then we get a better match between the geometries. Obviously, again, the different parameters were equal between the CFD and the earth basket type heat exchanger. So here you can see the depth on the x-axis, and here the temperature change on the y-axis, and then we've plotted it for the FLS solution and the CFD solution, and you can see this is just to show how the different rings, the different points that are closer or more distant from a specific ring in the Z dimension, in the depth dimension, how they match up. And you can see that we get a fairly good match between the rings in the CFD and the rings in the spirals in the CFD and the rings in the FLS in the analytical solution. So we are not introducing any errors because of a shift in depth and an error between the actual Z position and the difference between a completely horizontal ring or actually a slightly inclined helical turn of the total spiral. We can also plot it here, where we have the temperature calculated in the CFD simulation and the temperature calculated in the FLS, in the analytical solution. And you can see here that, well, let's say the angle, it's almost 1. So, you know, there's a very good match. And then there is a constant offset of around 0.2 degrees. So the overall error is on the order of 0.2 degrees Kelvin in absolute error, which is pretty good. Then we started making different parameterizations. So we matched up the reference case, which has been validated with the lab experiment, with the Earth Basket sandbox experiment. And then we now say, okay, we've got a pretty good match between the CFD and the FLS in this reference case. We also know that we can match up the CFD with the analytical solution in the geometry, in the space. And now we start looking at different parameters, like if we vary the heat injection rate, what happens with the error, the root mean square error? And it's not very surprising, but you can see that with increasing heat injection rate, the error increases as well in more or less a linear fashion. And we go to heat injection rates about 25 watts per meter, which in our opinion for the Earth Basket would already be quite a high heat injection rate. And you can see that even then in the steady state analysis, so this is completely steady state, we get an error of around 0.6 root mean square error. Here we looked at the soil thermal conductivity, and again, not very surprising, if the soil thermal conductivity increases, the error decreases, because obviously the temperature change near to the Earth baskets will be smaller as well. But again, we can see that in the range that we expect for an Earth basket, which will normally be installed in slightly saturated to unsaturated soils with a soil thermal conductivity not higher than 2 and more likely to be between 1 and 1.5. Again, the root mean square error between the CFD and the analytical solution is relatively small, between 0.5 and 0.3 Kelvin. Then we can also look at other aspects, things like the variations of pitch. Pitch is the distance between the subsequent rings or the subsequent turns of the helical shape. So if you have a high pitch, you have a big distance between, let's say, the pipes in the Earth basket heat exchangers that are at a different level in the ground. And if you have a small pitch, they're very close together. And then we've done that again for different heat injection rates, 5, 10, and 15 watts per meter. And here you can see that the change in that with very small pitch, we get a higher error because the pipes start affecting each other more. But with higher pitch rates, we get a smaller error again. We can also look at the radius of the ring itself, a large Earth basket or a small Earth basket between, let's say, slightly less than 20 centimeters. That would be a spiral, for instance, in a energy pile, and on the other hand, a radius of 0.7 meters, so a diameter of about 1.4 meters, which would be an Earth basket type like we've installed in the demo site. And again, you see that the root mean square error has a relation with the heat injection rate and also with the radius, but still the overall errors remain pretty small in the steady state analysis. The maximum one is slightly higher than 0.8 Kelvin. And then we are now also looking at not the steady state solution, but the transient solution. So here we look at how the error between the analytical and the CFD evolves as a function of time, of shorter time steps, because obviously the steady state, it's reached after a long period of time, but the actual operation of the system is in very short time steps, hours to tens of hours. So here we can see the result of the analytical solution, the red crosses, and the CFD, the blue balls, in a transient simulation between 50 and 250 hours. And here in the gray triangles, you can see the error, the absolute error plotted. And again, you can see the absolute error is very, very small. It is smaller than 0.04 Kelvin. So a pretty good match in this case. And then we're obviously looking at different cases, different number of rings, different pitches, different diameters, different thermal conductivities, and different heat injection rates as well. So I think, we've shown now that the analytical solution gives a pretty good solution of the performance of a earth basket type heat exchanger, and obviously the vertical borehole and slinky type heat exchanger have been validated as well against other existing software. And then we started using these analytical solutions to calculate performance analysis, to calculate what the performance of different type of heat exchanger is under different conditions. And then we're looking at construction parameters, but also at operational parameters. So the vertical borehole type, the slinky type, and the spiral earth basket type ground heat exchangers have been compared. And like I said, construction parameters and operational system behavior. And the operational system behavior has been done for different standardized buildings, like an office building or a residential type building, for different climate types, like northern climate, average climate, and southern climate, according to the European norm 14825, where the northern climate is based on Helsinki, the southern climate, the warm climate, based on Athens, and the average climate based on Strasbourg. And we looked at both offices and residential buildings in modern type buildings and retrofit situations. Then the first thing we looked at are construction parameters for ground heat exchangers in vertical borehole heat exchangers. And we took a look at the length, the borehole diameter, the shank spacing, that is the spacing between the U pipe going down and the U pipe going up, the pipe thermal conductivity, the backfilling thermal conductivity, so the thermal conductivity of the pipe material and the backfilling conductivity of the borehole backfilling, and also the soil thermal conductivity. And we made this comparison for a laminar and turbulent flow regime. And here you can see that especially shank spacing has a big effect. And second are like pipe thermal conductivity and backfilling thermal conductivity that also add to the effect on the thermal resistance of the borehole. So shank spacing is actually an important parameter to consider, especially in the laminar flow regime. In a turbulent flow regime, it becomes a smaller effect on the overall thermal resistance. If we take a little bit a closer look on the effect of the thermal resistance introduced by the pipe wall material itself, because of course you can think, can we use other types of material that have a higher thermal conductivity? So we zoomed in a little bit on that, and here you can see that we've considered different types of polyethylene material, different diameters of the pipe, different. The SDR, it stands for the standard dimension ratio. So it means that if you have a 40 millimeter pipe, the wall thickness is 40 divided by 11. Here we have a 40 millimeter type and the wall thickness is 40 divided by 17.6. So a thinner wall, and here a thicker wall. You get the pipe internal diameter, and then we get here the thermal resistance of the pipe wall material itself. And that varies, of course, depending on the diameter, 25, 32, or 40 millimeters, and the thickness of the wall. But then it's not, because this seems to be, a value, but what does it mean? The thermal resistance of the pipe wall, actually it means that it introduces a temperature difference between the fluid and the outer pipe wall that also depends on the heat flux, on the capacity that we are using the ground heat exchanger for. And that is the heat flux in watts per meter. So if we have a low heat flux, 5 watts per meter, or a very high heat flux, 40 watts per meter, the temperature difference, of course, as a function of the thermal resistance and the heat flux changes. And as the temperature difference introduces a performance reduction, and we know that this is about 2.5 to 3% per degree Kelvin, we can also calculate what our effect on the performance will be. So in this case, we can say that if we have a high temperature difference between the fluid and the outer pipe wall, then actually the effect of the pipe wall is significant. But if we have a lower heat flux, then the same thermal resistance of the pipe wall becomes much less of an issue. So here in orange and in red, we've indicated where this thermal resistance of the pipe wall itself will become a real issue and when not. And what you can see is that only in situations with a high flux rate, higher than 20 and approaching 40 watts per meter and relatively thick walls with SDR11, it becomes an issue, and you could think about using other materials to achieve a better performance. But in any case, the total effect is on the order of 4% in medium heat flux rates for vertical boreholes, and in shallow heat exchangers, it is even smaller because, as I've explained before, the thermal resistance is smaller even at low Reynolds numbers in helical type of situations, and we have an effect that is on the order of 2% or less. So this gives an indication how important the wall characteristics are in a heat exchanger. Then we started looking at other parameters, such as the radius of a ring, where we can have, for different soil conductivities, we can calculate what the effect is if the ring diameter increases or the radius of the ring increases. And we can see that there is a kind of cutoff where we say if the ring radius is above a certain value, let's say above between 0.5 and 1 meter, there is no additional effect of the ring radius. So we can say that there is a kind of minimum ring radius that is required to make sure that the radius itself is not negatively affecting our performance. We can also look at the soil thermal conductivity, and here we can see that at very low soil conductivity, like 0.5 in a completely dry sand, we have a big temperature effect of the soil thermal conductivity, but once it is above 1.5, this effect again decreases. So here we can say that if we have very dry soils, perhaps a horizontal shallow heat exchanger is of less, has a lower performance and needs a larger heat exchanger to accommodate the energy load than if you have a slightly higher thermal conductivity. And actually this is interesting because in one of the field test sites, they want to test this assumption by having, let's say, part of the shallow heat exchanger wetted, irrigated with water through porous pipes that have been installed as well, so that the effect of the moisture content on the thermal conductivity of the soil can also be measured in the field in a field study. Other things that we can look at as ring depth, and here you can see that the deeper the rings, the smaller the effect. So here also we can say we need a kind of minimum depth at which we want to install the ring, because at shallower depths we get both a bigger effect of the analytical solution using mirror sources, which is at very shallow depths not what we would like to have, but also the shallower you go, the more effect there is of seasonal temperature changes on the surface. And here we've looked at one ring solution, and one ring solution. And then if we look at the 10 ring solution, so 10 rings and then we vary the pitch, the distance between the rings, you can see here that already quite quickly there is no additional effect of larger distances between the rings, but we should have a pitch of about, well, slightly bigger than 0.3, 0.4 meters. And actually what we can see as well, that it does not really matter what the actual ring radius is, the effect of the pitch. So it's independent more or less of the actual radius of the ring itself. Looking at the spiral ground heat exchanger, these were for slinky type heat exchangers like I've indicated here. This is for the spiral type heat exchanger. Obviously, if we look at one ring, the situation will be exactly the same as for a slinky type. But if we look at pitch, then in a slinky type heat exchanger, there is a shift in the horizontal, whereas in a spiral earth basket type heat exchanger, it's a shift in the vertical. So it could be slightly different, but again, you see that at a pitch of around 0.3, 0.4 meters, there is no big effect anymore after that. So there is a kind of minimum pitch that we should consider for these type of heat exchangers. So for shallow ground heat exchangers, we can have these type of conclusions. The soil thermal conductivity should be around 1.5 watts per meter Kelvin or higher. If you don't do that, you have a bigger effect on the performance. The buried depth should be at least 1 meter. The minimum ring radius is around 0.6 meters. The pitch for a slinky type heat exchanger, at least 60% of the ring radius. And the pitch for an earth basket spiral type heat exchanger, at least 0.3 meters. Okay. And then we go to the system analysis. And again, here we've looked at a different type of buildings. This is retrofit residential. And then we have a slinky heat exchanger. We've also looked at vertical boreholes and at earth baskets. I'm not going to go through all the different variations with you because there are a lot of these analysis and graphs to consider, but just to give you an idea what we've been doing. We have a reference case that we've designed. So there is one standard design for this specific case, retrofit for cold climate in blue, retrofit for average climate in green, and retrofit for the warm climate in red. And then we started, with regard to this reference case, varying things like the peak load. So a higher capacity or a lower capacity. So here we have a lower capacity of the peak load by 25% and a lower capacity of the peak load by 50%. Then we've looked at the energy balance, the balance between heating and cooling. So 20% better balance for cooling and heating, or a 45% better balance for cooling or heating. And we've looked, for instance, at the trench, the distance between the different trenches that we need to install the slinky, because one trench is usually not enough. So if we have a distance between the trenches of 2.5 meters, or we have a distance between the trenches of 4.5 meters. And here you can see the relative effect of all those parameterizations. So for the cold climate, you can see that if we vary the peak load by 25% higher peak load, we increase obviously the total length of the system. For the 50%, it's even more. And then if we look at the balance, you can see that we reduce the length. For a higher balance, it's a slightly larger effect. And the trench depth also has an effect on the overall length required to achieve the same performance factor. The same we did for a slinky retrofit residential. Oh, there is a little bit wrong with the header here. This is actually not sure, because, okay, I'm sorry about that. I don't know exactly what this graph pertains to, because I did not put the correct header in it, but it's the same analysis, only showing slightly different results. Okay, then if there are no questions about this part, I will go to the engineering tool itself.
Yes,
so
Henk.
Yes, go. Yes, Marco, was there a question?
I confirm you can go.
Okay.
There is no question.
So this has all been quite a bit of theory, and we've put the theory into practice, let's say, and started creating an engineering tool. The engineering tool is based on Python as a programming language, and then we use Postgres as a database to store all the data, and Django as a kind of framework. So basically the whole tool has been implemented in a web type framework, kind of cloud-based system called the Ground Source Energy Designer, where you can log in and then start designing your project. At this stage, we're in, let's say, an advanced prototype phase where the interface has been developed and tested, but still some work needs to be done before we can put it into production. So we've organized the whole system around projects. So as a user, you can have one or more projects. But what we also did is we decoupled, for instance, the heat pumps from the project. So you can have one general heat pump catalog that you can use in all your projects. And another thing that we did was that every project can have one or more energy data profiles and one or more designs. So it makes it very easy to switch within one project between one energy data profile and another energy data profile, or to switch, for instance, between a vertical borehole heat exchanger and a slinky type heat exchanger and an earth basket type heat exchanger. So, once you've logged in this page, you can go to different pages where you have data that you can put in. Here, for instance, one of the case studies we have is the demo site with vertical heat exchangers in Sant Cugat in Spain. But we can also do the calculation then for an earth basket spiral heat exchanger for the same project. And here then you've different buttons that you can use to start different parts of the interface. I'm not going to talk too much about the engineering tool because it's just a lot of different screens and not very interesting. There are a lot of possibilities to edit the data, but some of the highlights are that we can do a direct calculation using the finite line source equations, but also do a G function calculation. The reason for this is in a different bullet because we can have ground heat exchangers, each with a different energy demand profile. So you can have neighboring systems with different energy demand. And then, of course, you cannot easily do that with a G function approach, but you have to use perhaps the direct FLS calculation to get that solution. We have vertical, horizontal, ring, and spiral type heat exchangers. We have taken care of project organization. Like I explained, we've decoupled the energy demand profile, the heat pump data, and the ground heat exchangers type so that it is easy to switch between them. It is also easy to copy a design and then just change the ground heat exchanger and carry out the calculations to compare different solutions. We have temperature-dependent fluid correlations. So if you've selected your fluid type internally, we can calculate the thermal conductivity, heat capacity, density, and viscosity of the fluid for different temperatures. And that means that in heating or cooling operation, you also get different correlations for the thermal resistance and pressure drop in the system. And we have implemented different calculations of critical Reynolds numbers, and we allow definition of transition zones so that the transition from laminar to turbulent is more smooth. And as I explained before, near surface seasonal temperature variations are included, as well as the deep geothermal gradients. So then again, if there are no questions about this part, we go to a part explaining the work that has been done on the actual ground source heat pump, because a ground heat exchanger by itself is usually not sufficient. We need a heat pump to translate the temperature from the source to the temperature in the emission system. And again, I would like to ask Michael to take care of this part, because it is also actually part of another work package 4, that AIT has been working on with the other partners in the project.
Yeah, thanks, Henk. So now it's another work package, but of course it's closely related also to the analysis of the ground surface, the ground source heat exchanger. So now we move this ground domain and take a look at the heat pumps as a connection element between the heat source, the ground, and the building. Yeah. So in GEOFIT we have, among others, we cover 2 different heat pump systems. So we have a so-called electrical driven or compression heat pump technology we take a look at. And the other technology is a so-called thermally driven, or we also call it absorption heat pump. So you will hear that in the next webinar more in detail. In GEOFIT, we have 5 pilot sites. Yeah? So we have a sports center, a swimming pool, we have a school, we have a residential building, we have a historic building, and we have a laboratory building, which is more or less a living lab, as you consider that. So out of those 5 pilots, we cover 3 pilots, the swimming pool, the school, and the residential building with the electrical driven heat pump or compression heat pump. And the other 2 pilots are established with the thermally driven heat pump. Yeah? That is the historic building and the lab facility. But you will hear about that, of course, more in detail on the training next week. Here, in that training, I will explain you a little the technology and how our approach was to develop together with the manufacturers those heat pump technologies. So it is both systems have novelty aspects in them, but when we talk generally, when we assume a correctly sized and configured ground heat exchanger, of course, a proper integration of such heat pumps in a retrofitting use case is a challenge. Yeah? And our approach in GEOFIT was in order to find the best solution for each pilot site, we analyzed different configurations because we have in the project strong R&D partners. That is the colleagues from CNR in Messina, Sicily, and it is AIT who teamed up with manufacturer and developed those new systems. So AIT was together with an Austrian company, Oxen Heat Pumps. So we developed the electrical driven heat pump, and CNR together with Fahrenheit, a German heat pump manufacturer, they took care of the thermally driven heat pump. So our approach from the R&D partners, so we have this model-based approach, which allows us to more or less, depends on how good our models are, and to do a precise and accurate component design. And it also makes us capable to establish control strategies. Yeah? Not only for the heat pump itself, but also for the entire system. So going from the ground heat exchanger to the heat pump to the building. Yeah. So we have the entire system, and yeah, it should help to minimize risks for not proper working heat pump systems. So we have this electrical driven heat pump, which is a compression heat pump, and the innovation here is the refrigerant. So we use a medium to low GWP, that's the global warming potential refrigerant to provide the heating, and the thermally driven heat pump, or also called hybrid heat pump. It calls hybrid because it consists sorry, it consists of a gas boiler, an adsorption unit, and a vapor compression unit. So the gas boiler here represents the heat source to drive the adsorption cycle. So not absorption, I mean adsorption, so not liquid, but a solid adsorption. So this is then coupled to a compression cycle for space heating and cooling. Yeah. So when we consider heat pump systems in general, and this is independent from the technology more or less, so we have some important regulations regarding our working fluid, and this is also one crucial issue we had to deal with in the project. So you might have heard about Montreal Protocol and also the Kyoto Protocol, which ban those CFCs, HCFCs, and so on. So what is that? This is the abbreviation for common refrigerants which have been used in the past, but due to their relatively high global warming potential, they should be banned to use in the future. One really important regulation is the so-called F-gas regulation, which deals with the phase down of refrigerants, and this phase down means by 2030 that the average permissible global warming potential in a newly installed heat pump system must be significantly below 500. Yeah? So the global warming potential is a number which you compare your global warming compared to CO2. Yeah? So taking a look at conventional refrigerants or refrigerants which have been used in the past, we are at the level of 1,000, 2,000, or even 4,000. So this value has to go down to below 500 in several steps up to 2030. Yeah, so that is 8 years from now, and it comes fast. So the component manufacturers and also the refrigerant manufacturers, they have to cope with such regulations, and in the same way of this phase down, okay, there are of course alternatives, but it's not really an alternative, but natural refrigerants, of course, they are getting a little more into focus because they have really low global warming potential. This brings me to the classification of refrigerants. So we have refrigerants which can be flammable and also toxic. And this is some groups which on the one hand side have a low global warming potential, but on the other hand side, they are flammable and toxic. And when taking into account heat pump systems with new refrigerants, we also have to deal with this classification. Using a flammable refrigerant, depending on the refrigerant charge you have in your system, you have to take measures. Let's say, for instance, proper ventilation, that non-flammable gases form with indoor installation. So this also affects the cost for your heat pump systems, which is of course an important number. So in GEOFIT, considering the electrical driven heat pump, here it is the configuration. Here's a trade-off, of course, between complexity of the machinery and efficient operation. Usually, of course, a complex system with a fancy refrigeration circuit is more efficient than a conventional, but it has the disadvantage of high invest costs. For instance, dealing with a retrofit use case, a favorable heat pump configuration can be a twin cycle, which is shown on the right here. A twin cycle configuration is basically two heat pumps in series on the supply side and in parallel on the source side, on the ground source side. So with two heat pumps, you are able to have a performance and an efficiency increase in a certain amount. But of course, it's two heat pumps compared to one heat pump, to a single stage heat pump. And one alternative is a single stage heat pump, which can use a significantly large condenser, which is shown here, having in mind a retrofit use case with higher supply temperatures, higher temperature spread on the heating side, which can make use of a higher subcooling, and for that higher subcooling increases performance. So this can be realized with a significantly large condenser for such enhanced subcooling. Both systems allow a more efficient operation than, let's say, a state-of-the-art compression heat pump in the case of the building retrofitting. And in the case of GEOFIT, we followed the approach of those large condenser. So this is with the manufacturer Oxna. So it's a heat pump with a standing cabinet. The compressor technology is a scroll compressor. The refrigerant is more or less a trade-off. We aimed for a really low GWP refrigerant. At that moment, it was not, let's say, allowed from the manufacturer. So we had to deal with R513A. So that is not a completely low GWP approach, but it is a medium GWP approach. Further, the superheating, subcooling, certain parameters, and so this is our approach for the electrical driven heat pump in GEOFIT. The thermally driven heat pump consists, as I mentioned before, of a gas-driven sorption heat pump. This system is coupled to a compression cycle in order to provide the heating and the cooling at high efficiency, and also making use of shallow ground source heat exchangers. Yeah? Because just generally speaking, those systems, thermally driven heat pumps, they have an inherently lower COP. COP is the coefficient of performance, which gives the amount of heating compared to the input you need to provide. So that is for, let's say, electrical driven heat pumps in a range between 3 to 5. Yeah? And here we have, for a thermally driven heat pump, we have lower COPs than for electrical driven heat pumps, which in turn also means that we have a low amount of heat at the evaporator. So we can use such systems with a smaller geothermal field, which is an advantage in terms of invest cost. Also, the requirements on the electric infrastructure are less strict as for electrical driven heat pumps. We, for instance, when we consider old settlements in rural areas, they have a limited connection power, and sometimes you cannot drive your compression heat pump with that boundary conditions. Further, for such thermally driven heat pump, it is possible to use an existing gas boiler to drive the system, as it says, thermally driven. So the coupling now, so this is the innovation, the coupling of an adsorption and a vapor compression unit within this hybrid heat pump system. This gives us a certain flexibility in operation modes. So in order to find the best solution for each pilot and also for the integration, the colleagues from CNR and from Fahrenheit, they have evaluated more or less 3 operation modes. So either direct heating with absorption heat pump, or indirect heating with gas boiler and backup, and cooling with the compression cycle. Yeah? So this is a short explanation of those 2 heat pump innovations within the GEOFIT project. So what we did, of course, when developing such systems, we go into the lab, as we did with the ground source heat exchanger. We also hooked up the heat pump prototype, which has been manufactured by Oxna, to the lab, and did a series of performance tests in order to characterize the heat pump and also to find optimization potential. Yeah? So here you see on the left this heat pump prototype built by Oxna with Michael Haas, a dear colleague from Oxna, which took the role within the project as an expert, of course, also on the heat pumps, but he gave important insights also in the integration of heat pump systems, the hydraulic integration into a heating system. Yeah. So putting that heat pump to the test stand, so the campaign was within, it was not completely a testing following the standards, the norm, but it was a testing following the conditions we foresee for the pilots, and we compared those testing points with our modeling, and we saw a good agreement, which we took further for the system simulations. Yeah, so we have a tested heat pump, and we have a validated model to that prototype. In the same way, there have been lab tests done by the colleagues from CNR in Messina, Sicily, with the prototype of the thermally driven heat pump. The thermally driven heat pump was tested, as you can see here, under those typical temperature evolutions. It is not a constant operation. Yeah? You always have to, it's a more a batch operation with desorbing, adsorbing the water in the solid. That's a type of zeolite. So it's a more complex system than the electrical driven heat pump. They did exhaustive testing in order to optimize the system and also find the proper operating conditions for the integration afterwards in the pilots. Yeah? So I'm showing now an integration example. I don't want to, it's a little teaser to next week's training, where you will find out more details about the pilots. So here as an integration example, it's called the Sant Cugat current system. Sant Cugat is the school, and the current system in the school that is near Barcelona. It consists of four gas boilers, some of them as backup, so not four are always running. So we have gas boilers, we have a certain header pipe here, and we have different heating zones. In total, 4 heating zones with those different building categories which are supplied by those heating zones. So now the approach is, okay, how to integrate a heat pump system there, because with existing systems, you have to deal with the distribution inside the building. So we have radiators, it's not floor heating, and we have different types of radiators. We have these older types, newer types. So to have the heat pump working efficiently, the correct flow rate and the correct hydraulics play at least a similar important role than the heat pump efficiency itself. Yeah? You can have the best heat pump, but when it's integrated not properly, you will not be happy with your overall performance of the system. So this is really important to take a look at the integration and find the correct components to change for the heat pump operation. And in that way, it was, of course, we need new radiator valves because we have now the heat pump operating at lower temperatures. We need new circulation pumps, balancing valves, of course, a storage tank, and here the heat pump. So this is, it's not a very detailed hydraulic layout, and this will be shown in next week. But things need to take care, not only heat pump, it's more than just placing a heat pump in an existing system. You need to take a look carefully on the flow rates and on your hydraulics in order to have an efficient operation. And this is what Henk has shown at the beginning of this training, that and the operating strategy plays an important role. So Henk already showed you this with those 3 operating modes. You can do it either by the heat pump alone, in either or operation, heat pump or gas boiler. But of course, in terms of efficiency and heat pump usage itself, and a parallel operation is favorable. Yeah, that you do the base load with the heat pump and just fire up the gas boiler when it's needed for really cold days. So in the end, with this parallel, bivalent parallel operation, you're able to do with a 40 kilowatt heat pump, you can go beyond 75% heat supply. Yeah, so you don't need to cover those installed 200 kilowatt gas capacity. Need to take care of the behavior, the occupation behavior, and also heat upgrades and so on. So small heat pump, still high heat supply possible, which of course is good for the business case. Yeah. So I think we go over to the field tests, Henk, when there's no question.
Thank you,
Michael. Yes, there is a question for you, Michael, from the audience, and they're asking your opinion about the use of propane in heat pumps.
Propane as a natural refrigerant, it is already often used in heat pumps, but it's more or less on monoblock heat pump systems where the entire refrigeration circuit is outside. Yeah, so you have for air source heat pumps. Yeah, you have the heat pump outside, and you just put with brine pipings, you go into the building because of the flammability of propane. Yeah? And I think speaking of thermodynamics, propane is a very good refrigerant. You can reach high COPs, a very good efficiency. When you have an indoor heat pump with propane, you just need to take care of the proper ventilation, and then I also think that propane can be used also with heat pumps inside buildings. Yeah.
Yeah, I can also tell a little bit about it. We were involved in a project, European research project, developing a propane heat pump with a ground source system. It was actually a heat pump that was used indoor. It was the GeoCool project. It was around a 17 kilowatt unit. Propane was used as a drop-in refrigerant for a heat pump that was normally running R134A. And we achieved over a 30% higher efficiency compared with 134A, and also with less than 500 grams of refrigerant, we had a capacity of around 16-17 kilowatts. So yeah, unfortunately, it was only the legislation that prevented the unit to be commercially developed. But as a refrigerant and as a system, it operated as a prototype for, I think, 8 or 9 years on the university demo site in Spain, and it actually performed very, very well.
Thanks for answering, and let me just remind you that we do have 10 more minutes to go.
That is good, Marco, because we're coming to the end of the presentations, and this is just a very short indication of field tests that are being also done within this project. And obviously, due to Corona and all the other delays we had, the demo sites are just online, so we don't have a lot of actual data at this stage, but hopefully we'll get more data in the coming weeks. But just a little bit an idea. This is one of the demo sites in Italy, Perugia, where a slinky type heat exchanger that you can see here has been installed. And here we have installed fiber optic temperature sensing cables. You can see here that we're doing also field calibration. This is the fiber optic cable, and we're collecting data there on the temperature evolution in and around the slinky type heat exchanger, to make sure that the distances are all equal, and that also we could attach the fiber optic. We've put in this grid with a metal framework, and then we run the fiber optic cables in a special way, because with the fiber optic measurement, the spatial resolution is limited, and we want to get temperature changes at relatively short distances. In this case, we also used a cheap fiber optic monitoring system, which means that the resolution it's not as high as with a very expensive one. Here we have a maximum resolution of about 1 meter. So what we did was we run the fiber optic cables in parallel to the slinky type heat exchanger. These short runs here are actually here, positioned here, outside the actual slinky field. So you can imagine that we go towards the undisturbed ground temperature. And then here we have the rows, parallel rows going on the actual slinky heat exchanger field. And by analyzing these consecutive meter distance measurements, we can get a good idea about how the whole temperature field evolves. Like I said, it's a relatively cheap fiber optic measurement system. It meant that we had to develop our own control and monitoring box for it, but that went very well with relatively cheap hardware. So that was actually quite interesting to do. And here you can see the map that we are doing, and you can see the temperatures changing on the different positions in the field. Here we see mainly the natural effect of the surface temperature over the different months of the year. The whole system has not yet been in operation in the measuring period that we've analyzed so far. Just a few tests have been running, but hopefully in the new data set that we're collecting now, we get better information with the heat pump running on the location. And then just to go on, the other demo site in France, in Bordeaux, where we've installed an earth basket type heat exchanger. Actually, 2 earth baskets have been installed here with an additional vertical borehole heat exchanger, because although sufficient space was available, there was underground infrastructure that prevented installing more earth baskets. So we've elected to go for a hybridized ground heat exchanger solution with 2 earth baskets and a vertical borehole heat exchanger. And you can see here my colleague Guus van Gelder working on installing the fiber optic cables and installing the actual heat exchanger in the ground. And here you can see one of the people from the French partner, Nobatec Romain, who is in charge of running that site. So with that, I'm coming to the end of this training session. And in summary, we've developed an integrated framework for the design of different type of ground heat exchangers, which has been validated, the new calculation methods based on laboratory experiments and computational fluid dynamic modeling, and at the end also using field tests. We have a complete toolkit now for all the different types of ground heat exchangers that can be used, a design manual for ground heat exchanger design. We've done a performance analysis for different types of ground heat exchangers, which will also help the engineer in selecting the appropriate technology. And we've looked at the cost-efficient heat pump system tailored for retrofit use cases. So this is basically the summary of the presentation that we've done so far. Then I just want to indicate a number of the results. This is the GeoFit, one of the GeoFit pictures of all the people involved in this work package. Something has dropped out. There should have been also a list of the publications that we've provided. Michael already indicated that there have been a number of master students working on this, on the toolkit as well. We had a master student, Chloe Meng, working on that. So several master theses have been published. They can be found on the website. And also, of course, I wanted to indicate that for the vertical boreholes and the slinkies, we've used existing literature from people like Eskilsson, Siminio, and also Spittler and Xiong from the United States, having developed the slinky type heat exchangers. So I wanted to reference to those publications, but for one reason or another, it's dropped out of this presentation. Thank you very much.